All right, so let's have a look at the final problem from homework 10. So here again, we have been given a system, and this time around we have to design a PD controller, which we haven't done so far. Uh, Everything else or the procedures that have been described are pretty similar to what we have been seeing so far, right? There is an overshoot value that has been prescribed. So we can make our root locus like we have been doing so far, and then we can take the overshoot of 20.5%, use this formula over here, calculate our damping ratio to be 0.4504, calculate the value of theta from that, and that turns out to be around 63.23 degrees. Again, since we will be using MATLAB for this, you can go ahead and plot this using the sgrid function in MATLAB itself. And from MATLAB, I ended up getting that the gain at this intersection is 1,140. And the location of this particular pole is this over here. And I have the MATLAB plot right over here. So yeah, so for an uncompensated system, we haven't added it yet. The intersection you can clearly see is at this pole over here, right? So let's go back. And so using that, as we had discussed for problem number 3, the real part of our pole is nothing but the product of the damping ratio times the natural frequency, right? So 2.91. And using that product or using this real axis component, we can directly calculate our settling time, TS. And so for our current problem, it turns out to be 1.37 seconds. Now, the criteria that they are telling us that we need to meet with our PD controller is to reduce our settling time by a factor of 4. So what we can do is we can set our new settling time to be nothing but the old settling time divided by 4. And you see that we end up with this expression over here, right? So the denominator here represents the real part of the pole of the new system that will allow us to reduce the settling time. So in a way, what we need to do to the point that we need to our root locus to pass through to get this new settling time is this over here. So this new point that a root locus should pass through, S star, is nothing but 4 times our old pole position, right? And this is what I end up getting. And so you can clearly see that this is now a new pole location. We don't know anything about our system yet, but we only know that the root locus of our new system, once we add in our PD controller, the root locus should pass through this point in order for us to meet the new settling time criteria. And in order to do that, let's go ahead and use one of the rules that we have been looking for so far. So our compensated system, as you can see, would look something like that. And for this compensated system, whenever we are drawing the root locus, this is one of the rules that we had discussed earlier on, that any point S on the root locus will always satisfy this criteria, that the sum of the angle that are made by the zeros minus the sum of the angles that are made by the poles is equal to odd multiples of pi. So let's use S star, which is the new pole position that we had evaluated, and plug that into this equation over here. So as you can see, we end up with this expression where the only unknown is the location of the zero for our PD controller, right? Over here. All the other locations are known beforehand. So we can plug in our new S star location coordinate system here, and then you can see that we have a bunch of these angles that we need to calculate. And as we had discussed in class, these angles can be evaluated with the tan inverse of having the imaginary part at the top and the real part at the bottom. So that's what I'm doing for each of these angles. So there is only this one tan inverse function that we can't calculate it, that we cannot calculate because we do not know the z. But all of the others we could evaluate, and we end up with this over here. So we end up with 1.6696 radians for tan inverse of this function here. And once we take the tan of this angle over here and do a little bit of algebra, we will finally see that we get our 0 to be at 9.3521. Now, something that I just want to point out here as caution is that make sure that the angles that you are calculating from the tan inverses and from that you're using on the right hand side here is in the same units. So if you are using 180 degrees here, make sure that all of your tan inverses also give you an answer in degrees. If it's pi, then make sure it's in radians. So basically, we now have a controller, a PD controller that would take this form. So we still don't know what the value of this gain should be, right? So in order to find out what the appropriate gain value is, what we can do is nothing but, as you guys know, the product of the gain times the transfer function at any particular pole location will be equal to 1. So a student did ask me about this. So shouldn't this be -1? And that is right. So the k times the transfer function is equal to -1. But here, since I'm kind of just taking the modulus just to figure out the positive gain value here, the signs are kind of being ignored as a matter of fact due to that. So we see that we end up with 694 as the gain that we need. So our final transfer function would be when we plug in 694 times s plus 9.3521. And this is what I've done in my MATLAB code, so I can show that to you quickly. So if you scroll down to problem 5, you can see that my compensator has been coded in like that. So I already have my 694 value of gain coded in. And because of that, something that I wanted to quickly point out, let me just clean this up, run this particular section. That is the step response that we would expect, but yeah. So this is the root locus. And if you were to plot a point that was at the intersection over here, perhaps I did not get the exact right intersection that I was looking for, but I already have a screenshot beforehand. So let's have a look at that. So there it is. So this is our new compensated root locus plot, right? And if you look at the intersection here, you see that the value of gain is 1. And that should not surprise or startle you because the gain of 694 has already been accounted for in the compensator over here, right? Which is why I have a gain of 1 at that intersection. If I had not plugged in the 694 over here, then you would perhaps see that gain coming up in the root locus plot as well. But since that has already been accounted for, you do not need to worry about it. And seeing this one should not make you think that you did something incorrectly. That's completely fine. And we can now compare the step responses of our compensated and uncompensated systems. You can clearly see here that the PD controller really improves this transient response of our system characteristic, right? The uncompensated system took quite a bit longer to reach its peak time, whereas the PD controller allowed it to reach that peak time much quicker. And that in a sense is why we use PD controllers. It's for improving the transient characteristics of the system. On the other hand, if you were using PI controllers, as you had seen from the other problems earlier on, or rather just problem 4 before this, we can help improve the steady state error. So both of those are kind of used to accomplish different things. One is to reduce steady state error, that is PI controllers, and one is to help improve transient responses, and that is these sort of PD controllers.